Okay, welcome to lecture 17th. So, what we were discussing in the previous class was stability of structures, and then we introduced the concept of dynamic stability. So, the reason to study dynamic stability is that sometimes we need to assess. So, of course, the obvious and the first reason is that we have to study the stability of the system under dynamic excitation, right. In a number of cases, the loading will be time dependent, then we cannot apply the static static formalism that we have derived, either energy based or equilibrium based, equilibrium equation based. Then we need to consider the inertia into account, or the kinetics also of the problem, right. And even before that, to start with, we can demonstrate a case in which, if you want to study this stability of the system using static method, you will see you will fail. Okay, the static method itself cannot solve the problem. So that's what we wanted to study. So then, and these particular classes of problem are the problem in which the force is non-conservative. Till now, whatever we have considered, all the forces, those are conservative forces, which were not causing any dissipation. Okay, you see. But here, this problem that we are currently taking into, looking into, here this force is non-conservative. I will explain to you how non-conservative, why the force is non-conservative. So here we are considering this problem was basically, many people try to solve it, but because they were using all static method, they were unable to solve it. And notably, it was the contribution for dynamic instability was made by Ziegler and Bolotin. Okay, Ziegler and Bolotin. So Bolotin has books on dynamic stability of structure. There is a very thin book, but it is a good book, good treatment of the subject. So you are considering a problem, and the problem we are considering a little different than whatever we have considered previously. In all the cases, we are considering the stability, static stability, namely buckling of column, in which the force were force was vertical, right, all the time. But here, the force is following the tangent, right. So that's why it was follower force. And then, with this kind of choice of coordinate system, we have seen. First, let us try to solve it using static method, and we have started solving in this previous class. So then, if it is following this, we are defining this angle phi, the tangent, and then we are writing down the bending moment at any section at a distance x, and bending moment, ei d2w dx2 is something like this. Capital delta is nothing but the deflection at the end, and then we basically obtain this equation, which is a linear differential equation with inhomogeneous with the right hand side term. So it will have complementary function and particular integral. Complementary function, of course, will be, because it's a d square plus lambda square, d operator will plus minus I lambda complex root, right. So it will be consistent of sine, cosine, the complementary function, and particular integral we have find out using operator, differential operator, and we obtain this is something like this, right. And then we enforce the boundary condition. There will be 4 boundary condition at x is equal to 0, no deflection and slope is 0, at x is equal to L at the end, T deflection is, deflection is delta, and then the slope is phi. Okay. So now, if we enforce all the, of course, you will see there are two C1, C2, delta, and phi, right. So let us enforce this, and let us obtain 4 equations. Let me write down the equation. Okay. So as you see, so first condition, if we enforce x is equal to 0, I am writing down the equation. Okay, 0 is equal to C1 into 0 plus C2 into 1 plus delta minus V into L. Then 0 is equal to C1 lambda plus C2 0 plus delta 0 minus P, this is 1. Then delta is equal to C1 sine, lambda L plus C2 cosine of lambda L plus delta minus phi 0, and then phi is equal to C1 lambda cosine of lambda L plus C2. You differentiate it, to enforce this one, C2, minus lambda sine lambda L plus lambda, 0 plus phi. So, 4 conditions, 4 equations, right? Fine. You can see this delta will cancel out, so delta multiplied by 0. Essentially, this gives you the 4 simultaneous equations and all are homogeneous system of equations. Now, let me write down in the matrix form. If you write in a matrix form, you will see writing in matrix form, so then we will get, okay, because although we have assumed that this is delta and this is phi, we do not know these values, right? Those are also unknown. So, then of course, for non-trivial solution, of course, the trivial solution will be all things should be 0, and in that case that will give you the fundamental path, but because then the system does remains in its equilibrium position, right. Let us see that if it has any non-trivial solution. For non-trivial solution, the determinant need to be 0, but its determinant of this matrix, if I take this matrix to be A, this determinant of this matrix A, you will see this is -1. It is never 0. For non-trivial solution, determinant must vanish. It is -1. What does it mean? That means there cannot be any non-trivial solution, right? There is no non-trivial solution. There is no non-trivial solution. What it implies? That implies that the system cannot lose its stability. The system cannot lose its stability, right? Because if there is no alternate configuration, if this system does not provide any non-trivial solution in perturbed configuration under follower force, it cannot lose its stability, right. Ultimately, any stability problem gives rise to a eigenvalue problem, right. Here also you can see, but what we are doing, we are following, once again here we are following equilibrium approach. We have considered the equilibrium in the deformed configuration, right. But we see that, so this, with this kind of approach, people actually were very confused, because they thought that, well, I mean, then what is the problem? That means under this kind of follower force, the column will never lose stability. So that gives a false notion, I am writing it down. So, on the fact that static method does not admit the existence of an alternative configuration it implies it implies that a column under follower force will never lose stability. It will never be unstable. That is wrong notion. This is a wrong notion also. This is a wrong notion or conclusion. Wrong notion or conclusion derived by static method. Arrived by static method. Static. Many people were confused, and then scientists were it was misleading. The static approach was misleading. That was giving it will never lose stability. That cannot happen. Okay. So the way that basically perplexed the scientist for quite several decades to see that this cannot lose stability, which is a wrong notion. Then people started applying kinetic method, and then with the kinetic method we will see that it really gives the correct solution, which admit that there indeed exists alternate configuration, and then it can still lose stability under the follower force. Let us do that. Let us solve the problem using dynamic method by incorporating the inertia force, okay, and by admitting by considering the kinetic of the problem as well. And I will tell you why this kinetic or dynamism in the problem, that is important to consider to reach at the correct conclusion. Okay. So for that, for simplification, for dynamic analysis, for simplification, so for simplification, we have assumed the distributed elasticity. We have considered the elasticity distributed, but let us assume that the mass is concentrated at its end. For simplification, mass of the column is assumed to be concentrated at the end. Concentrated at the tip of the column. So mass is m. I am considering the mass to be m. Okay. So this is the mass. Okay. This is the mass m. Okay. So then with this, what will happen? There will be little change. So this will also contribute in the moment, right? So if we consider once again, in addition to that, so whatever are the force, what was the forces, well, earlier, there is this P force, and then it's, horizontal component and vertical component, that is contributing in the moment, right? The way we write on the moment expression, the moment, so m x, right? So the way we have written is P into, so P into delta minus W, right? This one, then minus P L minus X, right? In addition to that, so these two forces are contributing, but if you consider inertia, then what this fellow will also be contributed? What? The inertia force, if the displacement in this direction, this inertia force is going to also act like this inertia. And what is the inertia force? I am assuming this mass. So mass m and then u double dot, right? Mass m into u double dot, right? And basically delta double dot. That's what we assume, right? So you please add this thing in the system. So here minus m is the concentrated force, m delta double dot means d2 capital D by dt2, right, and then that is the force. So, then once again you take the moment. So, then this moment will be L minus x, right. So, what was the additional thing that I am considering? I am considering the inertia of the column, and then the inertia was due to concentrated mass at that is assumed to be concentrated at the end. That is one kind of simplification. So, you have considered the mass to be concentrated at the tip, but the column has distributed elasticity, right. Okay, so with this, once again, moment is nothing but ei d2w dx d2w dt2 ei d2w dx2 is equal to p delta w minus p L minus x minus m d2 dt2 L minus x, right, or you just write it like this, d2w dx2 is equal to p ei minus p okay, like earlier the way we have solved it, d2w dx2 plus pi by lambda square w is equal to lambda square delta minus lambda square p L minus x minus this expression when you write m by ei. So, well, I mean, let us for the timing you write m by ei, d2w dt2 L minus x. So, that is the thing. Now, so once again there will one complementary solution and then their particular integral. Of course, the boundary condition let us define here. Boundary conditions will be wx is equal to 0 is 0, dw dx 0 0, these are at x is equal to 0, and then the other end w at x is equal to L, it is w, and then dw dx x is equal to L is equal to p, right. Note that it's a second order equation, so we can express the derivative until first. We don't require to have other boundary conditions defined, right? Fine. You can simplify this a little bit. This expression you can simplify it. You see that m by ei, we can write it m by ei is nothing but m by p and then p by ei. And p by ei is nothing but lambda square, so lambda square m by p. So, then we can write it like this. Of course, the solution now, we can write down the solution. The solution will be complementary function, and particularly once again complementary function will always be cos theta sin theta, right. C1, let me C1 sin lambda x plus C2 cosine of lambda x, and then here we can do one thing, then what we can do, for particular integral, see, particular integral will be 1 by d square plus lambda square, and then this one is lambda square delta lambda square c L minus x minus lambda square m upon phi L minus x into delta dt. So this part we have find it out, that's in a previous. So you just take lambda out and then you operate on it. Here for delta, what we will do, we can assume the solution to be delta is equal to delta 0 e to the power I omega t. That's what we can assume. Okay, e to the power I omega t. So because that will allows a what? Allow a which solution? It will allow a periodic solution, right? Isn't it? So similarly, so if we do this, then of course from here this term comes as lambda m by p L minus x, and this one double differentiate twice, so it will be minus omega square and delta 0 and e to the power I omega t. Okay, fine, e to the power I omega t, right? Now see, you may wonder that, well, there is only e to the power I omega t, but what you can do in the governing equation, when you assume the solution is in terms of w and there is p, right? So you can also assume that w also expressed as w0 e to the power I omega t, and phi delta is phi is also phi 0 e to the power I omega t. You see that? So for dynamics, this solution can be assumed, and if you substitute e to the power I omega t, term will cancel out from both sides, right? Understand what I am trying to? Okay. So what will remain here is basically is this term lambda square m p L minus x minus omega square delta 0. Okay, and then if you operate on this, 1 by so 1 by d square plus lambda square, you just operate on this, so it will be minus lambda square omega square m L minus x delta 0 by p. You just take lambda out. So if you take lambda out, 1 by lambda square 1 plus d square upon lambda square and things. So this lambda will cancel out, and then you basically take inverse of that and then you operate on this. Ultimately this term will remain. You understand how to find out the particular integral, right? So I am writing the final expression. Okay, so the final expression, the solution that you are going to get is expressed as in term. So I am removing this. So you already written. So w x is nothing but c1 so after reinforcing the boundary condition, enforcing the boundary condition, you will see the equation something like I am writing in matrix form. Okay, C1, C2 and delta and phi, right? Phi and delta, this form, right? And all the homogeneous boundary conditions, right? So is equal to 0, 0, 0, 0, and here let me write 0, 1, 1 plus m omega square L by lambda square EI, and this is minus 1 lambda 0 minus m omega square by lambda square EI minus 1 lambda cos lambda L minus lambda sin lambda L minus m omega square by lambda square EI 0 cosine lambda L, cosine of lambda L 0 0. Okay, you see that this is homogeneous systems of equation. Okay, now this, so essentially what we see, the addition of this inertia force, okay, in the previously, and then converting the problem into dynamic problem. Okay, we have assumed that all this W phi whatever was the variable, this follows this allows the periodic solution, right? You see that this we have assumed, and then we have substituted because W is both a function of x as well as a function of t, right? So then from there let us see whether it, once again this also gives rise to a eigenvalue problem, right? So determinant of this thing need to vanish for non-trivial solution. For non-trivial solution, this determinant of A, I am assuming this is matrix A to be 0, and then if you solve it, I am just directly writing this, if you solve it, then you will see omega to be omega square, rather omega square is P by small m L 1 divided by sine lambda L divided by lambda L minus cosine of lambda L. That is the value of omega square. So that means well, I mean, although the column doesn't buckle, loses its stability under static consideration, but dynamic constant it can lose stability for the given value of omega square. Okay, now so omega is depends on what? Axial force, that is being the force, the frequency of vibration, square of natural frequency of vibration will depend on the axial force, I mean the follower force magnitude P, because lambda is nothing but P by EI, lambda square is nothing but P by EI. So let us see how omega square changes, right? So when it will, see, as soon as omega is real, right, omega is real and then positive, it will give, it doesn't really matter, right, omega. As soon as it is real, it will give you what kind? The periodic solution, and periodic solution means it is stable, right? But if omega is in, omega square is negative, that means omega become imaginary, then what will happen? Then it will have what? It will have what? If it have this kind of value e to the power something like, if omega is imaginary, omega is I lambda, then I square, I square lambda t. I square lambda means, minus lambda t, right? Minus lambda t is still fine, because lambda t means, it will still decay, but it will not allow is the periodic solution. But if it is plus lambda t, then what will happen? It will decay, right? You understand? So that will indicate some kind of divergence, I mean some kind of instability. Let us see what happened to omega. Okay. So if you plot the value of omega square, then we will see that how it looks like. Okay. Let us So what we see that omega, omega square will be 0, and this is 0. Omega square will not be 0, omega square will be infinity, right? Infinity. When this is 0, denominator can always be 0, right? Here you see that when sine lambda L by lambda L minus cosine of lambda L is equal to 0, which does mean, tangent of lambda L is equal to lambda L. You see that? When tangent lambda L is equal to lambda N, which is once again the outcome of this, trigonometric eigenvalue problem, right? So what we see that for this condition, omega square will be infinity. That's what, do you understand that? This is increasing and going to infinity, and then suddenly there, and then from 0, see, initially it is positive, then for certain value it will be 0, then it will be negative. So you see that the omega square is positive, then suddenly it being infinity. When it is infinity, tan lambda L is equal to lambda, then it is changing like this. Then so once again it is being positive, minus infinity to it is being plus infinity, then it is something. So with varying p, omega square is changing its value. Omega square is being positive and omega square is being negative. Okay. Now when it is changing to going to infinity, that means it's, of course, it is instability, right? You understand, right? So the first this, so if you solve it, tan phi L is equal to phi L, how many roots will be there? So you can see this tangent, how it look like, the values of tangent, So these are the tangent, right? Look, this is the kind of function tangent look like, right? Isn't it? Huh? So tan pi by 2, tan 3 pi by 2, tan 5 pi by 2, isn't it? That's what is the tangent. This tangent function looks like this, negative also, right? So then lambda n, if you draw it, so this is the first root, this second root, this is the third root. That correspond, this root will give you the first critical load, P critical 1. This will give second critical load. This will give me first, third critical load. You see that? Isn't it? So then the first critical load where it is being infinity, right, from positive omega square, this is omega square is positive because this one is lesser than this one. So it is positive, so it is increasing, then it is being infinity, right? So what? PCR is equal to 1, this value, and PCR 1 is basically 20.19 EI by L square, because lambda L is equal to lambda L value is, I think, 4.54, okay. Yeah, lambda L is basically 4.4934, okay, and then lambda square means P by EI, L square is equal to whatever the square, 4.4934 square, and then P critical is being, same as, 20.19 EI upon L square. That is the value. Now what will happen when it is, so this is, and similarly second critical load also you can find out, okay. Now is this, don't you think this is much greater than the whatever pi square EI by 2L square by 4L square, if you, pi square EI 4L square is what? How much is that? Pi square EI by 4L square is nothing but 2.4649, 2.4649 EI upon L square, right? So it is almost like 10 times increase in the critical load. Look, you see, this is the first critical load, static buckling load, critical, P critical, static. So this is nothing but 2.4649 EI by L square. You see that 2.46. So this, so the dynamic, the follower, this load which one we get for the static, the for a column which is subjected to axial compression, it's not follower force, then respective critical load is how much? Pi square A by effective length is 2L to L square. So that's what is 2.4649. But this critical load is 20.1, almost 10 times increase when it is follower force. Why there is so much of increase? The so much of increase is, once again, let me tell you. This is because you see when it is follower force, then a component of it basically, see when it is vertically compressing it, then this is basically destabilizing moment, right? But for a follower force, component of this is stabilizing. You see that, right? And so is the inertia. So inertia, and then the component of the follower force is having a stabilizing effect on column. That's what it enhances the critical load for instability under follower force, and that's what lead to a 10 time increase in the critical load for the follower force. Understand that? Secondly, now you also think about the non-conservative. What is happening? That when this load is acting and this is deflection is occurring, right? So this load, see, this fellow is not working. Work done is what? Force multiplied by displacement along this direction, right? Okay. If the force is a vector and the displacement is a vector, so you take the cross product, right? If it is 90 degree, then cos 90 degree 0. So when it is vertically applied load, no work done is done. But when it is horizontally, this component is acting on this lateral deflection. So that basically is doing work, and that work is dissipating. That is that's why follower force is being non-conservative. We understand why follower force is non-conservative? Because a component of that follower force, which is in this case it is in a transverse of direction, that basically act on the lateral deflection to result into work done and thereby dissipation. That's what this follower force, the follower force is a that's why follower force is a non-conservative force. Clear? Now, so of course when omega square infinity, then it cannot vibrate, right? So this kind of instability is called flutter. So this kind of instability, dynamic instability is called flutter instability. So flutter is a dynamic instability. Omega square tending to infinity, plus minus omega plus infinity or minus infinity, okay? Flutter instability. And omega tending to 0 is called divergence instability. That I will talk with you later. What is divergence? See, you have done, so you understand flutter instability, and under follower force why it causes flutter instability, right? Now what is this? This is the frequency omega square when there is no axial force, P is equal to 0. And how will you get this thing? Well, you just expand this. If lambda, sin lambda by, let me explain to you, okay? We are doing this kind of simplification, and then you basically now you do u cos u plus sin u, expand it. You if you expand it, u minus u, so minus u, and then 1 minus u square by factorial 2 plus u to the power 4 by factorial 4, things, and plus u minus u cube of factorial 3 plus u to the power 4 upon factorial 5. From there, if you simplify, you will see that this is giving you u cube upon 3. U cube upon 3, okay, for very small u. very small u when p tending to 0, okay, for small u, huh? Small u means, small p as well, right? So then if you just simplify it, so this is omega square is equal to pi upon m lambda q and u upon 3. So it is the 3I upon m lambda upon uq is equal to 3I lambda u is equal to lambda u is nothing but lambda L cube. So 3I by m L cube. What does it mean? See, 3I by m L cube. What is 3I by L cube? If you take a cantilever, and there is a tip, load P, what is deflection? P L cube by 3I. So stiffness is what? 3I by L cube. Lateral stiffness is 3I by L cube, right? And you multiply it with the divide it with mass. So that is omega is root km. Do you see that this omega square, when there is no axial, no follower force, this is nothing but same as 3I by m L cube. Understand that? And I am proving it by doing this expansion. Clear? So Flutter instability, omega tending to infinity. So I will, go in much details, and later I will explain more, generalized things about Flutter. Right now, you try to see that this is a Flutter instability in which the frequency is jumping between plus infinity to minus infinity. Hence, it ceases the periodic solutions. Right now, another form of static instability, but it is manifested as a dynamic instability, is called divergence instability. So Flutter and divergence are the two most common of instability. But see, what is divergence? Divergence means you do not require to have even a follower force. You just consider the column which is under critical load. Okay, P critical. Now go back to your, beam which is subjected to critical load. Static. What is static deflection? Static deflection, it's out of plane deflection basically erodes. If there is axial force, it reduces softening of the system, right? Go back to your stiffness matrix and geometric stiffness matrix. At critical load, K minus Kg determinant becomes what? That's what determinant becomes 0, right? Isn't it? So if the stiffness, if there is no stiffness, what will be the frequency? If there is no stiffness, see, if you consider a column which is subjected to axial compression, no follower force, axial compression. If the load is below critical load or critical load for buckling, then still there will be some stiffness. But with increasing axial compression, its stiffness erodes, right? That's we have demonstrated both from beam column equation as well as geometric by formulating it in terms of stiffness matrix. I mean finite element matrix method, right? At critical load, it virtually erodes all the stiffness, right? And if there is no stiffness, frequency, stiffness, then what is frequency? Frequency becomes 0. And that frequency becomes 0 means what? That if it vibrate, will it allow it to vibrate? If there is no frequency, what will happen? What will happen? It will deflect in one direction, right? Right? 0 frequency, right? That is called divergence. That is called divergence. So divergence, although in dynamic sense it is called divergence, but divergence is nothing but a dynamic, dynamic equivalent of the static instability, buckling, right? So divergence is nothing but the manifestation of buckling. Okay, so it is in a dynamic term, right? Clear? Whereas Flutter is basically its frequency is never going to be 0, rather it is going to plus infinity to minus infinity. There are other things, okay. This is only for column and subjected to follower force, but I will explain to you how to identify, how you can, which will be Flutter and which will be divergence, okay. We have to see the change in frequency omega with follower force or any other forces, non-conservative forces. Follower force is just an example of non-conservative force, but there are other forces which are non-conservative. For example, follower force is the idealized force, but a bridge under aerodynamic, under flowing wind, bridge aerodynamics, okay, under a aerodynamic loading, that is also a non-conservative force. Hydrodynamic force is also a non-conservative force. So, you will see on those cases we will consider, instead of magnitude of the follower force, we will consider the magnitude of the wind speed, okay, as the control parameter. And there you will see we have to track the change in frequency with the increasing parameter which is triggering instability. And there you will see that flutter will be indicated by coalitions of mode and the coalitions and bifurcation of mode. So, the real part of frequency will indicate something and it will also reflected something in the imaginary part. Okay. Please note that here why it is going to infinity, because then the system does not have any damping. Omega is here, omega is here, when this is negative, omega will only be imaginary. There is no damping. If there were damping, it will never go to infinity, rather it will go to very large value. And if there were little damping, omega will not be purely imaginary, it will appear in complex, it will have complex value. So, omega square will be a plus minus IB, this form, if there were damping. So, you can see that real part basically represent damping, while the imaginary part represent basically the frequency at which it will vibrate. Okay, we will come there later, huh? Fine? Okay. So, now this is, you understand why do we require to study dynamic instability. Now, second, what we will do, we will consider a case in which is more familiar, you are more familiar with it, because this is a direct extension of the instability from the column buckling, because here instead of statically applied load, the axial force is being applied dynamically. That means it is a fluctuating axial force. So, column under axial pulsating load. Okay. So, column under pulsating load. Pulsating axial compression. Okay. So, here we consider the column, and this column is length L, EI, whatever length L, flexure rigidity EI, and it has mass per unit length to be mu. Mu is the mass per unit length. Mu is the mass per unit length. So, this column is subjected to force, a force, time dependent force. Part of it is static and part of it it's dynamic, cos omega t. You see that? So, P0 is the statically applied force and Pt is the amplitude of the dynamically applied load, Pt cos omega t. Okay. So, essentially why do you see this kind of force, a column which is subjected to this kind of excitation, why do you see this force? Of course, a column, you consider the bridge wear which is supporting the deck, and then maybe in the bridge where this is supporting two different deck, it's simply supported. Nowadays bridges are mostly continuous, so the vehicles are moving, the axially that dynamic load being applied, right, sudden dynamic load, right. Of course, that will not be continuous. Similarly, a column which is supporting some kind of rotating machinery, okay, so that also will apply this kind of axially pulsating force, right. Now, with this, what will be the equation of motion for this? You see, we know the beam column equation. What is beam column equation? Beam column equation is nothing but EI d4 W dx4 plus P d2 W dx2 is equal to 0. That is the beam column equation, or maybe laterally, if laterally applied load is there, then it will be something. This is the static beam column equation, right. Now, we have to add what? This is the static equation, right. We all derived that static on the static beam column equation, right. So, here inertia will come into picture. So, by adding inertia inertia to this equation. So, what will be? So, mu d2w dt2 plus here p will be p0 plus pt cos omega t, p0 plus pt cosine of omega t, and then plus ei d4w dx4 is equal to 0. That is the governing equation for, because this is inertia and this is basically the, well, here will be there d2w dx2. And because it will appear in partial because w is a function of x. So let me write it in partial. Okay, please. Partial. Now we have to solve this equation. How will you solve this equation? Oh, I mean, there are different ways to solve, but one thing, let us assume that this column is basically, it's a simply supported column. Okay, so that is for simplification. Okay, so you know, earlier we have, this is simply supported and there is also hinge, there hinge. So say, of course, it will, we must allow axial deformation, right? So then with this thing, what we can assume wx comma t, and we assume something like that, some, you know, maybe, you know, some term, you know, so fn, you know, fn t, and then sine, you know, n pi x upon L, something like that, n pi x upon L. Okay, n is equal to 1 to infinity. N pi x upon L means, you know, this will take the different, you know, harmonics in the sine. Of course, when you assume sine n pi x by L, it satisfies all the boundary conditions, right? So it's simply supported w is equal to 0, d2w dx2 is equal to 0, right? Here, please note that it's a fourth order derivative coming. So you have to consider shear force and bending moment, those things as well in the boundary condition. Okay. So simply supported, you know, hinge means what? W is equal to 0 and the bending moment is 0. So from there, so by satisfying both, you can assume this. So if you substitute it, you assume this kind of solution and then substituting, if you substitute what you are going to get, then let me write it down. You will going to get an equation something like this. So n is equal to 1 to infinity, you know, sine n pi x upon L, you know, del to f and del t to plus ei upon mu, you know, n to the power 4 pi to the power 4 divided by n to the power 4, you know, 1 minus L square divided by n square pi square pi p0 plus pt cos omega t fn is equal to 0. Okay. You see that if you differentiate, you know, with respect to time twice, you know, that's what you see it in time. So that's why double derivative is coming. And second, if you differentiate twice, you know, and then 4 times with respect to space coordinate, which is also sinusoidal, sine will remain sine. So that's what sine I am taking out. And of course, these coefficients will come L square and pi square ei coefficients. Okay. Fine, you just substitute and then do. I will simplify this. So then, what we see that we can take out the so from there, you know, I will, you know, the equation for the space we can take out. Okay, separately for the, you know, time equation we can take out separately, right? So then from here we can write down del to fn. I mean, I can use the, you know, total derivative also. So we do not require to then EI upon mu and n to the power 4, pi to the power 4, n to the power 4, L square this one. You can understand that this is pi square A by L square is nothing but PCR. Okay. Here also you can write PC. We will simplify this subsequently. Okay. And now we will use some certain quantity to simplify it. We will define critical load for nth mode as n square pi square EI upon L square. This is P critical, and then we can also define omega 0 square. Omega 0 is natural frequency, n to the power 4 pi to the power 4 pi L to the power 4 L square EI upon mu. Omega 0 square is the natural frequency in absence of axial force. Okay, and we also define. So then, if we define that, then this equation can further be simplified as del to Fn del T2 plus omega 0 square, omega 0 square, 1 minus P0 plus Pt sine omega t divided by P critical n, Fn is equal to 0. We will simplify it further, okay, the next class, but for the time being we will define this. So, this is the natural frequency in absence of axial force, omega 0 square. You can see this is a ratio of the K by M, right. So, this is elasticity and then this is the mass, right. So, then pi is coming, and critical load. So, if you simplify it something like this, further we will simplify it further, where we will consider the natural frequency in presence of axial force. So, omega 0 square 1 minus P0 by PCR we will define at omega n square and things like that. Next class we will do that. Okay. Thank you very much for today's class.